All right. Well, I am Garrett Tatum. I'm a fourth-year PhD candidate at The Ohio State University. Today, I'm going to be presenting some work that's been done in our lab group under Dr. Brenkus, assessing the durability of post-tensioning anchorage pourbacks. So the goal of this research is really to investigate how surface preparation and material choice impact the durability of concrete grout interfaces. So to kind of remind us of what this region looks like, I've put up a cross-section of what a post-tensioning anchorage zone looks like. And you'll see here in the gray, this would be the concrete beam that would continue on this direction with our post-tensioning tendon coming in here into the anchorage. Inside that tendon are these pre-stressing steel strands that end in this anchorage plate. That anchorage plate is then covered in a grout cap encased in grout to protect it from corrosion. And then the final corrosion protection measure is this pourback material. This is usually an epoxy grout that's put around the pourback as the final step to protect it from corrosion. This is what a post-tensioning anchorage from a bridge looks like in real life. You see the tendon coming out through this other end with the pre-stressing steel strands and the anchorage plate here. What this research is really targeted to is addressing the material interface between the pourback material in brown and the concrete substrate. Now I should note that this is specifically focused on looking at anchorage pourbacks and post-tensioning concrete, but really it can be applicable anywhere we have these material interfaces in our details that are used to protect metallic things from corrosion. And so there's a lot of different details in post-tensioning construction, and so there's a lot of different ways and places where we might use these material interfaces. As we talk about what durability really means, durability is kind of a function of three things. The dimensional stability of the pourback itself, the strength of the bond between the two materials, and the permeability of that interface region. So if we start thinking about the different levers or different things that we can specify that affect these different parameters, if we start talking about dimensional stability, the main thing that affects that is our material choice in the pourback. So we want to make sure that we choose a material that is non-shrink, has very low shrinkage, and is very dimensionally stable. As we get into the other two parameters, bond strength and permeability, this is a little bit more complicated as there's more factors that go into defining how these interfaces behave. The first is still material choice. What kind of material you choose is going to determine how that interface behaves. And then second is the surface preparation that you perform between the concrete substrate and the grout material. These two factors in turn affect the interface microstructure, and that microstructure in turn affects the bond strength and permeability. So this is really the crux of our research project. So I'm going to work through how we then evaluated each of these things. So looking at our experimental protocol, for our material choice, we chose to use a cementitious grout and an epoxy grout, both on a concrete substrate. We chose the cementitious grout because it's used in some other details in the post-tensioning system, particularly at vents and other places. Not super common to see that used in the anchorage region, but epoxy grout is the main material that we use there. So we pulled grouts used from DOT approved products list, primarily from Florida. And then we also pulled our surface preparation procedures from Florida DOT, Ohio DOT, and the PTI M50 document. So our different surface preparations are wet sandblasting at 3,000 psi nozzle pressure, water blasting, and we also included a no preparation group to simulate what the worst case scenario would be. Then to look at our different tests that we actually evaluated, we had the bond strength, which we evaluated using the direct tension or pull-off test. We evaluated permeability by chloride profiling, and we're working on characterizing the interface microstructure using SEM imaging. So I'll present some initial results with the caveat that this is ongoing. We've got results that are rolling in this week and everything, so just keep that in mind. First, let's look at the bond strength, the direct tension results. So on the y-axis here, you got the pull-off strength from that direct tension test. Most state DOTs specify a minimum pull-off strength of around 175 psi. So that's right around where this 1 bar is. On the x-axis, we have our two pour-back materials, our epoxy grout and our cementitious grout, and you see our different surface preparation groups there in the bar chart. For epoxy grout, we see that sand and water blasting had almost identical behavior. Cementitious grout, we saw a little bit better behavior with the water blasting, but also note the variability is very large. This is partially due to, you're testing concrete in tension, and so there's a lot of variability there. Also, this specific test method is kind of difficult to execute well, and so there's that. A couple other things I'll point out with the no prep group. Epoxy grout no prep maxed out our tester at around 580 psi. We're still evaluating what that is, what caused that. But as you might expect in the cementitious grout, the no prep group essentially had 0 pull-off strength. We've done several rounds of testing, and in each one, the cores that you get from preparing the test site all sheared off during coring and weren't even strong enough to make it through that, either through the vibrations or inadvertent shear or whatever they broke off before we were even able to test them. Now we'll move on to talking about chloride profiling. So this image here is the top of our test specimen. You can see the actual cylinder here. So we constructed this to have a simulated interface. The way that we did that, we took a concrete cylinder mold, cast concrete in half of it, cured it, and then used our surface preparation and cast grout in the other half of the material. So you'll notice we have 3 distinct regions within this sample, and we milled a profile to get samples from distinct depths in each one of these 3 regions, in the concrete, the grout, and the interface. Once we milled that profile, we measured the acid-soluble chloride content through the ASTM at each of those distinct depths, and used a nonlinear regression analysis to fit the concentration profile at different depths for our testing time. Inherent in this curve is the diffusion coefficient, which we heard a little bit about earlier. This is the primary fit parameter, if you will, in this curve, and it's an indicator of the durability of the system. So high diffusion coefficient means that chloride ions are easily able to travel through the system, which means that you get corrosion faster. And a lower diffusion coefficient means we have a more durable material that chloride ions are not easily able to travel through. So we did this chloride profile for each of our 3 regions of our sample: the concrete, the interface, and the grout, and for each of our surface preparations. So I will note we are performing the no prep interface testing this week. We just took them out of saltwater curing, so those aren't on here, but everything else is. You'll see on the y-axis we have the results of that fitting, the diffusion coefficient. Once again, a high diffusion coefficient usually indicates lower durability. So we see concrete has a diffusion coefficient on the order of 1.8 times 10 to the minus 8, which is acceptable. For epoxy grout, both of our grouts had very low diffusion coefficients. Epoxy grout had very close to 0. It's likely because it's a completely different material, different microstructure, different capillary structure than our cementitious grout. In epoxy grout, we see that our water-blasted interface group had a higher diffusion coefficient than either of the constitutive materials, indicating that something inherent in the interface region was causing faster diffusion than in the constitutive materials. For cementitious grouts, the diffusion coefficients were fairly close, but slightly above the average of the 2 constitutive materials. Now, I want to try to illustrate the difficulty of directly correlating the permeability and the pull-off strength. So here on the y-axis, I'm trying to put these two parameters together. So on the y-axis, you have the diffusion coefficient that we just looked at, and on the x-axis, you have the pull-off strength that we were looking at just a moment ago. And we see two opposite trends for our different materials. For epoxy grout, we see that the water blast, we see a variation in diffusion coefficient, but almost no variation in pull-off strength. But the reverse is true in cementitious grout, where we have high variability in pull-off strength, but not much variability in diffusion coefficient. So we're trying to, what we need now is a more mechanistic approach to understand what's really driving these factors, which is why we're choosing to look at the interface microstructure. The way that we're evaluating this is through some scanning electron microscopy imaging. So we're looking at three parameters here: the topography of the interface region, the composition of the materials in the interface region, and the porosity around that region. So you'll see here, this is a backscatter electron image here of our interface sample, where this interface is aligned between here. So through this imaging process, we can see how the surface preparation actually affects the depth of the concrete through EDS mapping, which is another sensor that you insert into the microscope. We can estimate the composition and map the composition throughout the sample. So for instance, this yellow particle here is mostly silica, so we can say that that's a sand particle. But through this composition mapping, we can evaluate how the surface preparation and the materials are behaving along that interface between our experimental groups. And finally, once you get that EDS map, you can use the different values and compositions and perform some thresholding to detect where are the voids, where are the different materials, and then we can evaluate the porosity specifically at that interface line and in the surrounding materials close to it. So putting these three things together of topography, composition, and porosity, we're hoping to get a more mechanistic understanding of what's happening at these material interfaces at the microstructure level. So some preliminary conclusions. We've got, once again, we're evaluating surface preparations and material choices on the durability of our interfaces. So far, we found that surface preparation does not play a large role in chloride diffusion at epoxy grout interfaces. It does play a large role in diffusion at epoxy grout interfaces, but not so much at cementitious grout. And also that bond strength does not directly correlate with permeability, so that we need more microstructure assessment of what's actually going on. We need generally more abrasive surface preparation is desirable, especially for epoxy grout. That's why we saw that huge decrease in diffusion coefficient. But finally, like properly constructed interfaces can be just as durable as the constitutive materials. As we're continuing to work on this, we're working on the microstructure imaging. Right now, we're continuing work on doing more pull-off and chloride profiling, and we're working towards using these to develop a durable pour-back criteria. And with that, I'm happy to take any questions. I'll note that this work was funded by ACI, so glad to be presenting that here.